soon. Bling. Okay. So if we think about translational motion, what was the condition for equilibrium? What did all of our forces have to be equal to? 0.
0.
Now, when we say that, though, we have to be specific. We're not just saying the forces are all 0, right? Because if I had this, let's look at the right example. It says a sign is suspended using ropes as shown in the diagram. If the tension 1 is 100 newtons, what is the weight of the sign? Right there, they're telling us a force that's not 0. So really what we're saying is not that each force is 0, but that the total force, or the sum of forces, is 0. This sign that I've just drawn here, that's sigma. You all heard of sigma? I think it's on your formula chart. They use it there. But it's basically the Greek symbol, which means sum. Pretty much you add them all up. In calculus, you'll learn all about it. Sigma. Typically, it's written a little bit fancier than the way I write it. I write it kind of like the shorthand lazy version. If you look in like your textbook, a lot of times it'll look like this. It'll kind of have like a little hook on the front, and then go down like that. But like the lazy version is just right like this.
Use it in chemistry.
Yes, probably for what are y'all doing right now?
We're finishing up the equilibrium stuff.
Yeah.
Oh, we're doing kinetics.
Y'all are not doing calorimetry stuff, I assume? That was honors, probably.
We did some, but I missed that earlier.
There you go. So this is something you'll see in other fields for sure, especially in calculus, though, once you start doing limits and such like that. So thinking about the sum of forces, we could also reason that the sum of forces in the x direction and the sum of forces in the y direction have to also both equal what? 0. Because what are we in? What's the word of the day? Equilibrium.
Equilibrium.
All about that equilibrium. So going to my diagram, let's draw some forces. The way we work any problem is first and foremost, we have to choose a point in the system that's in equilibrium. So what would be a good point to pick? Adam, what do you think we would pick on this diagram here? Where is a place where all the forces are acting on something? Okay, so in the point where they all attach here, so maybe we could say the intersection. I like that, Adam. That's good. And if we go to the intersection point, I could draw a few forces here. We could have T1. We could have T2. And then we could have what would be going straight down here from the sign. Yeah, it's FG. Technically, it's T3, which is generated by FG, but let's just call it FG. All right, we're smart enough to reason through that. So that would be my 3 forces. Now, step 2, it says draw a. What did we just draw?
Free body diagram.
Yeah, free body diagram. FBD, forces, diagram. Then step 3, this is where things get interesting. We got to break the forces into the components. Absolutely, into the X and Y components. And then we just have to use a little bit of math. Typically, we're going to use a little bit of, I'm seeing angles. What are we probably going to use? Oh yeah, cosine, sine, and tangent, baby. So if you're not good at trig, because like, I don't know, we had a global pandemic and then you didn't learn that because you were not there or something, it's okay. We're gonna go through that. I know some of you are in that camp. Now let's take this diagram, let's add a little bit to it. Let's do step 3. How do I break these forces into components? Let's do T1, a little dashed line here, going out. And let's call that T1x. And we can do the same thing going straight up, and we could call it what? T1 y, absolutely. And I can do the same thing for T2. I can draw T2 dashed line straight up, call it T2y. And I can do the same thing to the right here and call it T2x. So all I'm doing is I'm breaking these components into their, into these vectors into their component parts. And by doing so, what do you think we're going to do with T1x and T2x? Any ideas? We're going to set them equal to each other. Because if they're the only 2 things pulling apart, they have to balance, right? And what do you notice about T1y and T2y?
They're opposing FG, so those two added together equal FG.
Ta-da, we're done here. So we're going to add these up and set them equal to FG. But before we can do that, all we know is T1 is 100 newtons. So pretty much we're going to have to solve two triangles. Okay, two trigonometric functions. It's going to be okay. We're going to do it. I can hold your hand. It's easy. Let's do it together. So I'm going to scooch the paper down and we're going to draw the triangle. Okay, triangle one. We're going to pick on T1 first. Okay, T1. We did him. Was that the blue or the green one? I think it was the blue one. I hope so. So T1 looked like this. And so we had T1y right here, T1x here. Okay. What angle did they give me?
55, where T1 and TX
Where did it go,
intersect.
Pargavi? Keep saying? Between?
The tension 1 and then TX.
Perfect, right there, 55 degrees. Thank you. So if that's the case, and I know T1 is 100 newtons, can I find my other sides?
Yes, you can use sine.
Okay, remember sine is opposite over hypotenuse. So if I'm looking at the sine of this angle, 55, T1y would help me there. So that'd be T1 times the sine of 55. Now I'm going to show the full version just right here in the corner, just in case. If you can't do this, it's okay. If you need to write SOHCAHTOA and then look, okay, I've got an angle. I'm looking opposite that angle right there. And I have the hypotenuse. So I know I'm using sine. So if I write the sine of theta, you don't have to do this if you don't want to. It goes opposite over hypotenuse. That means the sine of my angle, 55, is equal to the opposite, which is T1y, over the hypotenuse, T1, which means T1 sine of 55 equals T1y. That's what we just wrote right here. Okay, that's the step-by-step, though. If you need to do that, you can do that. It's okay. I literally still write SOHCAHTOA on my paper, and I think about it when I go through these. It is okay to do that. So if I do that, that's math. That we can just plug it into a calculator. That gives us that T1y is equal to 81.92. I'm going to do the math for you today so that on Thursday you can do all the math for yourself after we talk to work. T1x, that would be T1. Instead of sine, since I'm talking about the x, which is adjacent, what would I use? PJ, what am I going to use there for this adjacent side? Definitely cosine. Good choice. Which means I'm going to have 100 times the cosine of 55, which is 57.36. So now I know that that is T1x. So I found T1x and I found T1y. Sweet. Okay, let's talk about x for just a second. We did this on the diagram, but let's make sure it's very explicit. The sum of forces in the x direction. Look back up at your diagram. Thinking about T2x and T1x, which one of those should we treat as positive?
The one that's going rightward,
Which is which one?
TX2.
Very good. So T2x. And if that one's positive, Luke, what am I going to do with T1x?
Subtract it from.
Whoa. I called on Luke. Sorry, Pargavi. What am I going to have to do, Luke? Because if we just said this one's positive because it's to the right, T1x, which is to the left, we're going to have to subtract it exactly. But take it to the next step then, Luke. If that's the case and that's equal to 0, what does that mean about T2x, Luke? Thank you. It has to equal T1x. So this is the mathematical proof of what we said when we were looking at the diagram. That's perfect. Which means that we can actually just solve it. T2x has got to be the answer we just found, 57.36 newtons. Okay. Let's just pause here for a second. All get caught up on the same page. Laziness for the win. Where do we go from here? Nicole, where are you thinking we should go? We found T1x, we found T2x, we found T1y. What should we probably find next? We found both x's and we have one of the y's.
FG. Wait, no. T1Y plus T2Y.
Yes. Think back to, that's kind of the, put that down here somewhere. The sum of forces in the y direction is what we're working towards. So she is correct there. We have T1Y plus T2Y minus FG is all equal to 0, which means T1Y plus T2Y equals FG. This is the ultimate goal. Keep that in sight, because if we look at that, I know T1Y, it's right here, but I don't know T2Y. So in order to find FG, the weight of the sign, that's kind of the ultimate question, then I need to find T2Y. So let's draw T2. I'm going to do him back in green. Here's T2. We'll draw T2Y and T2X. Who have I not picked on today? Megan, I know you're gone yesterday, but which of these do I know?
Like the angle?
Yes, the angle.
Which I'm sorry, it's 45 degrees.
Very good. We know this is 25 degrees. And we just found that T2X was 57.36. Very good. So if that is the case, we have a side and we have an angle. Is there a trig function that allows me to find this opposite side over here with the adjacent side? Bargavy, what would I use there?
We're finding T2Y.
We're finding T2Y and we have the adjacent side. So we're looking for opposite. We have the adjacent. We have the angle.
Couldn't we use tan?
Absolutely. The last one, how convenient. So the tangent of theta would be equal to opposite. So opposite my 25 is T2Y over the adjacent, which is my T2X. That's 57.36. Sorry, let me write that fully. You can leave it if you already wrote that, but I'm just going to put it over to T2X, which means that T2Y is 57.36 times the tangent of 25. Which means T2Y is equal to, this is a lot of work, 26.75. Now,
Well, this is just the final weight.
this is just to find the weight of the sign. So what do we do, Cality? Bring us home. We've got T1Y up here. We just found T2Y. What's all I have to do right here? But what do I do? Add them up. We're done. So let's do it. 81.92 plus 26.75 equals the weight of the sign FG, which is, I get 109 newtons. Yes, plug and chug.
That sucks.
It was rough. But what have we learned?
That we hate trig.
Besides that we hate trig, BJ. Yes, we all dislike trig, except those of us who enjoy pain and also like to do stoichiometry for fun. I love it. But what is, think back to the original question. You're missing the point. The original question was, a sign is suspended using ropes as shown in the diagram. If the tension is 100 newtons, what is the weight of the sign? What have I learned as a shop owner hanging a sign? This is your real world application. You're all like, oh, physics is dumb. I don't learn anything. It's simple. Okay, you own your business. You're hanging a sign. You just found the weight of the sign is 109 newtons. What does that mean?
It's heavy.
It's heavy. What if I wanted to upgrade my sign and hang a 200 newton sign? Why? What would I have to do, Maddie? Two options.
Better string.
Just Maddie. Better string is an option. Or what? How can I change the angles, Maddie, do you think, to increase the weight that I can? Just Maddie. Think about the angles. Notice the left one had 100 newtons of force in it. The right one has less force. So what if would I increase or decrease the angles of the ropes to support more weight, do you think? Absolutely. Because the more vertical my ropes are, the more force they can support. Exactly right. This is your take-home moment. Think about that. When you're owning your boutique or your store one day and you're painting a sign and someone's trying to hang it really, really flat level, you would want it hanging straight down. Most signs you see hung are at 90-degree angles, or they're on a pillar at a 90-degree angle, right? Because that's the strongest. Interesting. Okay. Questions on that? Trig. It's hard, but you just have to practice. Okay, let's take a brain break. This is the brain break called the number 5. So let me explain how this works. You're gonna have to partner up, and it's kind of tricky. So I'll use Coley just as an example here so you can see me, at least people at home. Okay, if we were face to face, I'm gonna be partner A, you're gonna be partner B, okay? Partner A is going to raise their arm and point in one of the directions of the clock. So like 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'm gonna stick up a finger between 0 and 5. So for example, if I hold up a 1 in the 12 o'clock position, Coley is gonna put 4 in the 6 o'clock position. Okay, so she's gonna do the mirror image and our hands have to add up to the number 5. That's why the brain break is called 5. So we'll do that. And then she's gonna choose the direction and the number. So she's doing 2 over there now, so I have to do 3 over here. So she is currently in the, that would be what, 9 o'clock position. So I have to go to the 9 o'clock position and hold up 3. So basically I'm doing the mirror image and then adding the 5. Does that make sense? And then we alternate just back and forth. You try to go as fast as possible. So partner up at each table. Let's try it. It's not too bad. You do have to stand up though. Stand up and give it a shot. If you're really good, you can do both hands at the same time. You can do different directions. Pass that up to 5. There you go. So alternate A, then B, then B, then A. People at home, y'all can try this if you want. Let me stop presenting so you can see each other better. Y'all can like partner up, just Prezi and Austin, Shanae and Alex, Barnaby and Geraldine, and then shoot, Nick, you and Austin, it looks like is gone. So partner up, pick a person and try to do that mirror image with them. Geraldine, if you and Nick want to do it, it looks like Barnaby and Prezi are already up. Man, y'all are killing it. This is good. Try to do 2 hands at the same time if you can also. Like 2, 1, and 3. 2 hands is like next level, y'all. Try it. You have to do, you would do 4 to the left. If you were doing 1 here, she would do 4 there.
Yeah, she was.
Ah, I see.
I'm also supposed to choose numbers, Barnaby.
I feel like I'm like an eye doctor. I'm like, can you see my finger here? Can you see it here? Follow my finger. Tell me when it doubles. All right, very good. Trig is our weakness, but clocks, it turns out, is our ultimate weakness. We like digital clocks. All right, let's learn strategy 2. So some of you, you like what we just did for whatever reason. Your brain works like mine, where you think X, Y, and you equate them. Others are going to prefer this method. So let's go on to number 2. We present the screen so y'all can see it. Okay, let's do the closed vector diagram method. To me, this way is a little more tricky. To you, you might like it. So let's see. What we have to remember is, since we know that F net is 0 at any point in equilibrium, what would happen if we added up all the force vectors? They would add up to what, Kelly? They would add up to 0. That's exactly right. Because they add up to 0, I can use the sine law, the cosine law, or any other means, Pythagorean theorem for all I care, to solve the triangle. However, big star here, never, ever, ever assume that it is a blank unless you can prove it geometrically. Prezi, what goes on the blank?
A triangle?
What kind of triangle?
A right triangle.
Thank you. Never assume it is a right triangle unless you can prove it. And by prove it, we mean look at the angle, see if they add up to 180, and it fits. For example, here we have a 35, a 50, and a blank angle. And this, so is this a 90 degree? No, these add to 85. So if I do 180 minus 85, I would actually have 95 degrees. So that looks like a right triangle, but this is why a lot of times on the AP test it'll say, note, figure not drawn to scale, or note, don't assume it's a right triangle. They will never say that, but you just have to remember, don't assume. So let's do this. This is going to be painful, but it's going to be okay. How many of y'all know how to do the law of sines?
Probably just-
Y'all just learned this? How convenient. Weird. So thinking about the genius that I am, I waited until y'all learned this in pre-cal. Just kidding. Totally random luck. Typically, we'll be doing circular motion when they do unit circle, and then we do kind of parallel here as well. This year it happened to line up, which is a good thing. So if you've learned it already, that's good. If you haven't, it's okay. If you're in Algebra 2, here you go. The law of sines is basically looking at angles and sides of a triangle. So here, if you looked at, we have a side and an angle, but FG is straight down right here. So we're actually gonna have to draw a new triangle. We would have T2, let me change colors here. The T1 over here, and let me go back to red for FG, I like that best. FG in red straight down here. Let me just erase that, looks terrible. Okay, thinking about that, we would have to then add our vectors. So if I think about the sum of forces total, let's just add the forces. Add FG, add tension 1, add tension 2. It should all add up to what? 0. Good, Callie. When in doubt, today's answer is 0. Okay, last week's or 2 weeks ago, I guess, the answer was always towards the center of the circle, right? Remember that? So let's draw T2. I'm actually make mine a little bigger because I want another room here. So T2, literally the same size. FG, what was our method for adding vectors? Something about tip to tail, right? Tip to tail. So I go to the tip of the vector and then I draw the next tail. Then I go tail to tip, down, that would be FG. That's an ugly triangle, holy crap. Sorry, my hand glitched. There we go, that's a little better. And then where is T1 going to be drawn? Right back across, right? Make a nice triangle. Not a right triangle, though. Yikes. So we have a complex triangle here. Let's think about the angles. They tell me that this is 50 degrees between T2 and the ceiling. So if I think about, like, almost imagine the ceiling here. Draw yourself a little perpendicular line. That means that this is 50. What would this have to be? Because
180 minus 50 plus 35.
Whoa. FG is what to the ceiling? Perpendicular. So we can assume this is a 90-degree angle, which means this actually would be 40 degrees. Otherwise, yes, we could look at the other side here and try to solve backwards. But it's easier to just think FG is perpendicular, so that total angle is 90 degrees. That we can prove. What about at the base here? Think about if I'm looking at T1. They give me this is 35 degrees. So what would this angle here have to be?
35 as well.
No. This would be 35, which means this would be 55, right? Because alternate interior angles, this would be 35 degrees here, which means this angle between my perpendicular FG and this would have to be, if you extend this up, it has to be 90-degree total, which means 90 minus 35 for 55. And that leaves us finally here with how much? We would do 180 minus 55 minus 40. So how much would I have left over? 85, yeah. Degrees. Okay, so this is where I'm now going to use the law of sines. How do I do the law of sines? Prezi, I think, did you put it in the chat, didn't you? Oh, I saw that. Yes. So we're going to do the LOL flashbacks. C over the sine of C type of thing. Pretty much what we do is let's pick a side. Let's pick T1 for an example. So if we do T1 divided by the sine of what angle is across from T1? You're good.
85. Or sorry, 40.
So opposite T1 is 40. Yes. And then that's going to be equal to FG. I'm picking FG because they gave me this 64 newtons over the sine of The angle
85.
opposite FG, which is 85. Thank you. Perfect. So that means that T1 is equal to FG sine of 40 divided by sine of 85. And that's a number. It gives us an answer of 41 newtons.
So that's a simpler way.
Some people think it's a simpler way. I think they're both hard, but that's okay. Physics is hard and everything doesn't make sense. This is more aesthetically pleasing to me because it makes a nice weird triangle. Then when we do T2, let me change colors. Oh shoot, I just did T1 in blue. What was I thinking? I should have done it in green. Oh, that's awkward. Let's change it to something totally random like orange. So T2 now, boy, that looks like FG though. That's gonna be confusing. Let's do this ugly teal. It's kind of greenish. Oh well. T2. Can y'all see that? Okay. T2 over the sine of what side is opposite T2? 55, which is going to be equal to FG over sine of 85. Same thing here. T2 equals FG sine of 55 over sine of 85. That's a 5, which is 53. So we're done. Take home message. Which force is bigger and why? T1 or T2? Looking for a hand. Goalie. T2 because it's more vertical. That's it. So if we were looking to check ourselves, we see this answer is bigger. We see a bigger angle here. It makes sense that it should have more of the force, quote unquote, on rope 2. Real world application. Let's say I only have so much of this rope, and then or maybe I'm hanging it with like fishing line or something. I don't know. If I have a really weak pound test line, like a 12-pound test, and then I have like a 30-pound braided, which side am I going to put on the T2? The braided fishing line, because it can support a lot more strength, right? If you're not a fisherman, if you're a fisherwoman, perhaps the braided is like the green string that y'all use. So on like pulleys and things that we've done some labs with, is really strong. It doesn't stretch. On the other hand, T1 would be more like when we use the yarn. And what happens when we spin the yarn really fast? Wasn't that in this period? It stretches, it breaks, and it flies off and almost kills someone with a stopper. So we don't want that to happen with the sign, because if the sign falls and kills one of our customers, what happens? Lawsuit, we go out of business, and then we lose all of our money. So sorry if that strikes a personal tone. I don't know if anyone's lost anyone in a tragic sign accident. Hopefully not. So PJ, last question.
Where did you get the 40 for sine 40?
The sine of 40 came from, basically I looked at this T1, and then straight across from it is this angle, 40 degrees. Pretty much the way that they'll learn it in the maths class, they do like A, B, C, and then little a, little b, little c. So the law, the way it kind of works is you put A over the sine. Oh shoot, I did this wrong. Sure did. Idiot. Sorry, that's why I don't teach math, y'all. I teach physics. This is A, this is B, this is C. So A over the sine of A, because it's opposite, is equal to B over the sine of B. I learned this like one time in math class, and then I had to relearn it when I started teaching physics, because I was just like, I know I've done the law of sines, but I don't remember how to obey the law of sines. So I had to go to math jail. We do law of cosines too. It's very rarely will show up for our class though. So that is that. Okay, let's take off the training wheel, shall we? Approaching a hill, here you go. Whee! I'm shoving you down the hill. It says an object is suspended as shown. If the tension in one of the ropes is 50 newtons, what is the weight of the object? Hint. Draw your free body diagram. Think about components. And then when you're done, check with people around you. I'm going to stop the recording because this is our last one. We'll let y'all practice. Baseball, gentlemen, hopefully you're watching us on the way to Granbury. Good luck.
We're on their way back.
Yeah, maybe so.